Welcome to The Explainer. Today we're taking a fascinating zoom-in journey straight from the everyday smartphones in our pockets right down to the microscopic, invisible digital highways that are literally filling the air around us. We use our mobile devices constantly, but we rarely stop to think about the sheer engineering miracle happening right in front of our faces, or I should say, in the empty space between our screens and the nearest cell tower.
Seriously, just imagine millions of people in a single city using the exact same airwaves simultaneously. You've got one person managing critical healthcare data, another's deep into an intense online game, and dozens more are hailing rides via GPS apps. How is it that not a single call overlaps? How do all these invisible signals magically stay in their own lanes without crossing paths? Well, that is exactly what we're going to decode today.
So here's our roadmap for this journey. First, we'll look at the magic of mobile computing. Then, we'll trace the evolution from 1G to 5G. After that, we'll figure out how we actually share these invisible airwaves, followed by how we control all that network traffic. And finally, we'll wrap up by comparing the multiple access technologies that make it all happen.
Okay, Section 1, the mobile computing magic, connecting anytime, anywhere. Let's dive right in by defining what mobile computing actually is. At its core, it's the ultimate combination of three things: mobile devices, like our phones, wireless communication networks, like Wi-Fi, and software apps. Together, they have one profound goal: granting us access to data, voice, and video anytime and anywhere, even while we're on the move.
And this technology has become absolutely ubiquitous. The average person checks their phone over 100 times a day. It powers literally everything in our modern lives. Think about it: daily communication through messaging, education via e-learning, secure mobile banking, and even remote office access. It's a real game changer in healthcare too, powering life-saving telemedicine. Whether you're tracking a rideshare, streaming HD video, or relying on critical military and disaster rescue operations, none of it exists without mobile computing.
Moving right along to Section 2, evolution from 1G to 5G, the generational leap. Now, this seamless mobile magic didn't just happen overnight. To get to a point where you can instantly stream a movie in the back of a moving car, we needed some massive, generational leaps in infrastructure.
Walking chronologically through these leaps is honestly pretty staggering. We started with 1G, right? That meant carrying around a massive, heavy brick of a phone just for low-quality analog voice calls, with basically zero security. Then came 2G, shifting us to digital, bringing better voice quality, encryption, and the very first text messages. 3G revolutionized everything with high-speed mobile internet and video calls. Then 4G LTE arrived, giving us the speeds needed for HD streaming and online gaming. And finally, today's 5G networks bring ultra-low latency and incredibly high bandwidth. And it's not just for phones anymore. 5G is designed to connect the Internet of Things and power entire smart cities.
Which brings us to Section 3, sharing the invisible airwaves, multiplexing, and spread spectrum. So, the absolute crucial point here is understanding how the network handles all this immense generational traffic without everything colliding in midair.
The answer begins with a brilliant engineering concept known as multiplexing. Basically, multiplexing is the ultimate trick for maximizing space. Imagine you have a single, invisible digital highway. Instead of letting just one massive truck hog the entire road, multiplexing figures out how to pack multiple lanes of fast-moving data traffic onto that exact same single channel. It is a massive boost to bandwidth utilization and overall efficiency.
So, engineers pull off this multiplexing trick in three main ways. First up is frequency division multiplexing, or FDM. Think of this like painting literal separate lanes on our highway. Different signals get their own dedicated frequency ranges. Next is time division multiplexing, or TDM. Picture a rigidly scheduled conference room. Different users share the exact same channel, but they get specific rotating time slots to speak. And the third is code division multiplexing, CDM. This one is super fascinating. It's like having multiple pairs of people in the exact same room, all talking at the same time, but they don't interrupt each other because each pair is speaking a totally different, unique language over the exact same frequency.
But hey, dividing up the airwaves isn't just about fitting more people in. It's also about keeping those signals safe and reliable. And that brings us to spread spectrum. This is a wireless technique where, instead of sending a signal on one narrow, easy-to-block path, the signal is spread out over a very wide frequency band. This clever little method makes the communication highly secure, incredibly reliable, and heavily resistant to outside interference.
Now, there are two really distinct ways signals protect themselves using spread spectrum. First, We have frequency hopping spread spectrum, or FSSS. Just like the name implies, the signal rapidly changes and hops around between different frequencies. It makes it incredibly hard to intercept or jam. Then there's direct sequence spread spectrum, or DSSS. Instead of hopping around, the signal uses a special secret code sequence to spread itself out wide. It effectively hides in plain sight alongside other noise, but comes through perfectly clear to the intended receiver who holds the right key.
All right, Section 4, Controlling the Network Traffic, the Role of MAC Protocols. As we zoom in even further from the highways and the lanes, we find the strict, invisible rules that keep all these multiplex signals polite and organized at the device level.
These rules are governed by MAC protocols, which stands for Medium Access Control. You can really think of MAC protocols as the ultimate digital traffic cops. They're like the polite rules of dinner conversation that step in to govern exactly how devices access and share the communication channel. Without them, absolute chaos. Thousands of devices trying to talk at the exact same time would just result in massive data collisions.
Think about this for a second. Your ability to instantly download a movie on 5G is entirely reliant on these highly disciplined, rigid underlying rules. MAC protocols are constantly working behind the scenes. They handle channel access control, actively avoid data collisions, provide error control, and ensure fair communication for every single device. To pull this off, they use a whole toolkit of strategies, ranging from contention-based protocols to controlled access to strict channelization protocols, just to keep network efficiency running smoothly.
And that brings us to our final section, Section 5, Comparing Multiple Access Tech, SDMA, TDMA, FDMA, and CDMA. Let's zoom right down to the most microscopic level to see exactly how physical spaces, times, and frequencies are mathematically divided up for all of us trying to access the network at once.
Let's start by comparing SDMA and TDMA. Space Division Multiple Access, or SDMA, simply separates users geographically, often using directional antennas on cellular towers to serve different areas and bump up capacity. Then we have Time Division Multiple Access, TDMA. Remember our timeline from earlier? Well, TDMA was actually the backbone used in those 2G GSM networks. It allows users to efficiently share the exact same frequency bandwidth, but drastically reduces interference by mathematically dividing up access into rapid-fire, tiny different time slots.
Now let's look at FDMA and CDMA. Drawing a direct line back to our history again, Frequency Division Multiple Access, FDMA, is what powered those clunky 1G analog systems. It's a pretty simple implementation, where users are just assigned different continuous frequency bands. On the flip side, Code Division Multiple Access, CDMA, is what brought massive capacity to the 3G mobile revolution. With CDMA, users actually share the exact same frequency in the exact same time, but they use highly secure, unique codes to prevent any interference.
So think of this matrix as the ultimate cheat sheet for our journey today. It takes an incredibly complex web of telecommunications engineering and distills it into 3 clear rules. FDMA gives us simple communication by separating frequencies, TDMA gives us efficient bandwidth by separating time slots, and CDMA gives us high security and massive capacity by using unique codes. Together with multiplexing and MAC protocols, these technologies form the absolute bedrock of the wireless communication systems powering our world.
As we wrap up this explainer, I want to leave you with a final thought. We've seen how insanely intricate the rules of mobile computing have to be just to manage the transition from 1G to 5G. But with 5G now actively connecting entire smart cities and the Internet of Things with ultra-low latency, what incredibly complex, invisible rules are going to need to be written when our future leaps from billions to literally trillions of connected devices talking all at once in the 6G era? Just think about that the next time you seamlessly stream a video from the palm of your hand.